I want to explain more about this idea of a mole and how we can actually find this little n, this number of moles of a gas or a substance if we need to. So let's start by looking at this number again, this 6.022 times 10 to the power 3. Let's have a look and see how this number came about. This number, right, the official definition today is sort of evolved over history, has a name. Okay, this number has a name. It is called the Avogadro constant. I believe it's named after the person who first found out this value, but the definition has changed a bit over history, and today it is defined as let me write down the symbol. You could use N, capital N with a subscript capital A to represent this number. It saves you from having to write out so many digits all the time. So this Avogadro constant is defined as the number of atoms, okay, in 12 grams of carbon 12. Make this more clearly. Carbon 12. Now, if you're seeing this for the first time, it will look very odd. Why carbon 12? How in the world did this come about? Well, actually, I don't know. I don't know why carbon 12. There must be historical and scientific reasons for that. Now, but what I'm going to explain is how, from this definition, we can get some understanding of how to use this constant, how to use it correctly and confidently for our calculations, like with ideal gas problems. So let's start from the carbon 12. Let's start by understanding what this means. Okay, carbon 12. What is carbon 12? Well, carbon 12. Well, we sort of know what carbon is. Carbon is like when you burn a piece of wood and it goes black, or you burn your food when you cook, it goes black. That's the black stuff. Is carbon. Actually, it's got a lot of other chemicals inside, but okay, the main stuff would probably be carbon, and happens in your pencil, what you would call a pencil lead, and it's also in diamond. So it's all carbon there. But what does the 12 mean specifically? Okay. The 12 here means this. Imagine a carbon 12 atom. Carbon 12 atom, an atom, if you've learned about the structures in an atom before, an atom has protons inside and it has neutrons inside. Right? And it has electrons around it. So that's an atom. And we're talking about the mass of the material now. So let's think about the mass of the atoms. So the mass of the atoms made out of the mass of each of these separate particles, but the mass of each electron is very small. It's 2,000 times smaller compared to the mass of the protons and the neutrons. So we would usually, when considering the mass of an atom, it's usually okay, quite safe to ignore the masses of the electrons. So let's just look at the masses of the protons and the neutrons. Right, so inside there we have two types of particles inside the center of the atom. We have protons and we have neutrons. Now for now, we don't worry about the difference between these two yet. That will be in a later topic. But for now, let's just think that both of them have the same masses. Right, both of them have the same masses, and in a carbon 12 atom is an atom that has let's see, I'll use C for carbon. This is the carbon atom. The carbon 12 atom is an atom that has 12 protons. That has 6 protons and 6 neutrons. It has 6 protons and 6 neutrons. And the 6 protons and 6 neutrons and protons have very nearly equal masses. Okay, so there are altogether 6 of these, and the 12 here is just the total number of this. And then you might ask, so why not just call it carbon? Why do we have to carry the word 12 along? I mean, if carbon atoms always have 6 protons and 6 neutrons, then just call it carbon. Yeah, we're not interested in the 6 and 6 neutrons all the time. That's fine, except that in this case, in order to clearly define this number of atoms in 12 grams of carbon, we can't just leave out the 12 for one simple reason, because it is also possible for a carbon atom to have 14 protons and neutrons. If you have ever heard of something called carbon-14 dating that they use in archaeology to where they use the radioactivity of carbon-14 to find out the age of something that they dig up from the ground that are thousands of years old. That would be carbon-14. So it is also possible for a carbon atom to have 6 protons and 8 neutrons. That would make it a total of 14 particles, 14 of these protons and neutrons at the center. Okay. So this is called an isotope of carbon. But again, we'll talk about that later. So that's why we need to specify the carbon 12, because the carbon 14 will clearly be heavier. Okay, now if you have 12 grams of carbon 12 atoms, that specifies precisely the type of carbon atoms that we want, and therefore the mass that we are talking about. And then if you then specify 12 grams of this kind of atoms, then you can be sure that you're always talking about the same number of these atoms. And that number, that after what must have been lots of measurements, experiments, theories and arguments among scientists for most of the last century, very accurate values of this number has been measured today, which you can find by searching on the internet. And the value that we use today for our, say, physics and also chemistry is this value, 6.022 times 10 to the power 23. So that's the number in this number of this mass of carbon 12 atom. Fine. So that's the definition of the Avogadro constant and this number. But so what has that got to do with this oxygen and this ideal gas? So we'll look at that now. Oxygen. Okay, have a look at oxygen. the oxygen molecule. Now an oxygen atom, so let's say the oxygen molecule is made up of 2 oxygen atoms. O2 has 2 oxygen atoms. Now each oxygen atom, okay, an oxygen atom is not so different from, if you can actually see with your own eye what the atom is. It's actually not so different. Doesn't look so different from a carbon atom. It's got protons inside the center, neutrons inside the center, and it's got electrons, a number of electrons around it. So that's our everyday oxygen atom. Okay, but there's a slight, what looks like a slight difference. There are 8 protons in the center, and there are 8 neutrons. 8 neutrons. So if I want to be as precise as I did for the carbon atom, I would say oxygen 16 atom. So that's an oxygen 16, and there are actually oxygen 18 and oxygen atoms with slightly different number of neutrons, but the proton number must always be the same. For the same elements, the carbon must always have 6 protons. Oxygen must always have 8 protons, even though the neutrons can be a little bit different. Okay, so that's my oxygen atoms, and there are actually 8 protons and 8 neutrons. Now compare this with the carbon atom. It's the same proton we are talking about. All right, you don't get a different type of protons in a different element. All right, protons are exactly the same. Neutrons are exactly the same. So protons and neutrons are the building blocks. It's like the Lego pieces, if you like, or the bricks that we use to make houses. The same bricks can make houses of different shape. So the same protons and neutrons make atoms of different elements, exact same ones. So each proton in the carbon has the same mass as each proton or neutron in the oxygen. And what I'm trying to say here is that if all you need, if you look at the total number, this number 12 here or the number 16 here, which by the way is called the atomic number. It's called the mass number. Just forget that. Okay, right. Anyway, if you look at this number here, this mass number would be, this number should be proportional to the mass of the atoms. Proportional to the mass of the atoms. Okay. Now you see, now you might begin to see why in the definition of Avogadro constant they pick the number 12. Because it so happens that carbon has 12 protons and neutrons. So that's why they pick the number 12 in grams. Okay? Because of this reasoning, because of this coincidence, 12 grams for carbon 12 atoms would have 1 mole of particles, this number of particles. And because I know that the protons and neutrons in oxygen are the same, exact same kinds of protons and neutrons in carbon atom, because there's only one kind in the universe. So therefore, the ratio of the masses of the carbon and oxygen atom is 16:12. 16:12. Okay, so that's for one. So one atom has this number of protons and neutrons. So therefore, if I have, instead of for 12 grams of carbon 12 atoms, I know that I have this number of carbon atoms. So what if I want the same number of carbon of oxygen atoms? Right? If let's say I have 16 grams of oxygen atom, if I have 16 grams of oxygen 16 atoms, I must therefore have the same number of atoms as there are in 12 grams of carbon at 12 atoms. So 16 grams of oxygen, 16 atoms, all right, has this number of atoms, 6.022 times 10 to the power 23 atoms. So that makes it convenient. All I need, if I want to find out about the number of atoms, is that I will start from the fact that if I have an oxygen 16, if I know that the atomic mass is 16, then I just add the word gram next to it, and 16 grams of that would have this Avogadro constant number of atoms. Now let's take this idea to the molecule. Now the molecule has 2 oxygen atoms. If I want to count the molecules, okay, the molecular mass this time, or if I would be just the total number of protons and neutrons in there. But in one oxygen there are 16 protons and neutrons, so the molecular mass of O2, the molecular mass, right, in units of the weights of protons and neutrons, would be 2 times 16, which is 32. Okay, so just take the word the unit gram next to this, and we know that 32 grams, in 32 grams of oxygen molecule, there must be this Avogadro constant number of oxygen molecules. So let me summarize this. Let me clear this out first. Okay, so let me write down this result. In let's see, so what is called the relative molecular mass of O2 is 32. Now this is roughly the same as, this is very nearly the same as the number of protons and neutrons. There is a more precise definition of relative molecular mass in chemistry, physics also, maybe in a later session that I shan't go into. But taking this 32 as the number of protons and neutrons, if that helps, if you're given this number, then all we need, if you want to find 0.1 gram of the number of moles in 0.1 gram of O2, is to make use of this idea. From this knowledge and the definition of the Avogadro constant, it means that 32 grams of O2 has this number of particles. It has 6.022 times 10 to the power 23 molecules. So what about 0.1 grams? So 0.1 gram of O2 has, so all I need is to take the fraction, and multiply by this, has 0.1 gram over 32 times the Avogadro constant, 6.022 times 10 to the power 23 molecules. So what if I have another gas? Well, if I have N2, for example, or maybe CO2, let's say I have CO2, the relative molecular mass is 44, okay, then instead of 32, I would need to change this to 44. Instead of O2, if I have CO2, then 44 grams of CO2 will have the same number of molecules. Okay, and if I want to find 0.1 gram of CO2, then I would have to change that number there to 32 to 44.